Hey everybody. Today we're talking about random variables. Intuitively, a random variable is just a variable whose value is determined by a random process. In terms of notation, we typically use capital letters to represent the random variables themselves, and the corresponding lowercase values to represent particular, but typically unspecified, values of those random variables. A few examples of random variables: the total on the roll of 2 dice, the number of flips of a coin until you get the third head, the exact height of a randomly chosen resident of Chicago. Now, not all outcomes of probability experiments are random variables. For instance, the sex of a randomly selected puppy at a dog shelter, or the eye color of a randomly chosen U.S. senator. While these are random occurrences, the outcomes are not numerical. On the other hand, not all numerical things are random variables. For instance, the total number of steps in the building where you live, or the temperature in New York City at noon today. Neither one of these two things are random occurrences, even though they are numerical. A bit more technically, given a probability experiment with a sample space S, a random variable x is a function that maps an event E to a real number x. For instance, if we flip a coin 5 times, or if we flip 5 coins, we might let x of E be the number of heads observed. And under this definition, which is the more technical one, a random variable is neither random nor a variable. Random variables fundamentally come in 2 flavors, continuous and discrete. A continuous random variable can have outcomes in a range of values, like the length of a geyser eruption, randomly selected geyser eruption, or the exact height of a randomly selected person. The outcomes of a discrete random variable, on the other hand, can be listed. For instance, the total on the roll of a pair of dice, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or the total number of coin flips needed to obtain the third head. Notice that in that second case, there isn't an upper bound on the number of flips that you might need. It can be 3, 4, 5, or any number greater than that. So a discrete random variable does not need to have a finite sample space. A couple of examples. I recommend trying these before seeing my answers. First of all, a book is chosen at random from the Library of Congress, and X is going to represent the total number of pages in that book. This is an example of a discrete random variable. The number of pages in the book might be 1, 2, 3, 4, 5, etc., but I don't think we're going to talk about a book with 1.5 pages. Another example, let Y be the rainfall in millimeters on a randomly selected day in New York City. We'll consider this one to be continuous. Even though we're measuring in millimeters, we could certainly have decimals or fractions of millimeters. The distinction between discrete and continuous random variables becomes really important when we begin to assign probabilities. When we're talking about a discrete random variable, we can just list the outcomes and their probabilities, and we call that correspondence a probability mass function. It just takes every possible value and assigns a probability. When we're talking about a continuous random variable, on the other hand, that won't work because the outcomes can't just be written down in a list. In that case, we instead resort to a probability density function, which assigns probabilities to every possible range of values, typically using a definite integral. For instance, suppose customers at a particular restaurant give ratings on a scale of 1 to 5 stars, with relative frequencies shown in this histogram. So for instance, 6% of customers are assigning a rating of 1 star. Let's let a random variable x be the number of stars assigned by a randomly selected customer. So we have about 6% of customers giving 1 star, so we'll have a probability mass function that assigns f of 1 equals 0.06, f of 2 equals 0.08, and so on. One more definition as we wrap up. The support of a random variable x is the set of all possible values. So it's the set of all x values with a probability mass function or probability density function that's strictly greater than 0. In that last example, the support was the set x equals 1, 2, 3, 4, and 5, because those are the values that have non-zero probabilities for that random variable.